use, I think we can at least partially address the concern of phosphate rock depletion and the mitigation of potential manure phosphorus the negative impact on our environment. I'll take thank you. Yeah, we'll take dairy industry as example. So the table 1 shows the estimate typical manure characteristic as excreted. So this is from SAB manure standards. So mature lactating cows that generate roughly 70 kilo manure every day. On this manure, they have almost half kilo nitrogen and 100 gram of phosphorus and potassium. So take the right one shows the top 10 the milk production states in the USA. We'll take either as example, in 2024, we have 663,000 cows. We even don't count the 1.7 in California, 1.3 million in Wisconsin. So almost all the 10 top states have a couple 100,000 cows. If we time this 600,000 something with 365 times 100 grams, that's definitely is a significant amount of phosphorus in the manure. The number of the technology have been tested to better recycle phosphorus. We just heard the cyanobacteria fertilizer products for manure yesterday by Brian from Wisconsin. And there are different technologies. I think the hydrothermal carbonization process we call HTC is one of the promising technology, has gained a lot of attention in the past years. The HTC is basically a thermochemical conversion process for the organic matter into a carbonaceous products. So the HTC takes place in an enclosed environment under mild temperature around 180 to 255 degrees C, and the pressure could be in 1.2 to 4.5 megapascal. And one of the good things the HTC, it can directly to process wet matter or liquid flume. See the manure is one of these things without pre-drying. So the carbonaceous solid products is commonly referred as a hydrochar, which is different from the biochar. It's a solid product for the paralysis of solid feedstock under much higher temperature. So our study investigated the potential of phosphorus recycling through the hydrochar production. We use lab scale and bench scale, the HTC prototype system. We just target the liquid manure here directly from our commercial farm. I hope to get some the soil amendment. So to study the phosphorus transformation in the HTC process, first we did the experiment use a lab scale reactor as shown here with 300 milliliter volume, right? The goal is to investigate how the operating temperature and the reaction time affect the hydrochar yield and the phosphorus recovery. So the hydrochar yield will based on the dry weight of the char and the dry weight of the raw manure. Regarding the phosphorus recovery, we use the total phosphorus, how much in the total phosphorus in the produced hydrochar and the total phosphorus in raw manure. This experiments were carried out at 3 temperature, 200, 225, and 250 degrees C with reaction time 30, 60, 90 minutes. We use a 3x3 factorial design with a duplicated run per condition. This is the observation from the lab scale studies. The top right one is the hydrochar yield. So we can See on the horizontal, the HTC 200-30, that means temperature 200, the reaction time 30 minutes. So we see with higher temperature, the longer reaction time, basically the hydrochar yield is reduced, kind of clear trend. Look at the left side is the phosphorus distribution. During the whole HTC process, basically they convert the non-appetite inorganic phosphorus, mainly the iron and aluminum bound phosphorus and organic phosphorus, to the appetite P, mainly the calcium bound phosphorus. So with higher temperature, longer time, we see have more this non-appetite organic phosphorus turn to the appetite, the calcium bound phosphorus. That's supposed to is a no release finite resource. In terms of the P recovery, with the increased temperature, longer time, I will show you next slide, the hydrochar, the content, the total phosphorus in the hydrochar have a higher value. But considering the reduced hydrochar yield, so we notice the optimum operating condition within our test boundary, in fact, is the temperature 225 with a 60 minutes reaction time. We get a higher phosphorus recovery. So here is the nutrient distribution in the hydrochar. We only, I guess, monitor this nutrient, the total phosphorus, ammonium nitrogen, and the nitrogen, and the calcium, potassium, magnesium, and the sodium. So the first 9 is raw manure. You see, with increase the temperature and the time, basically the hydrochar contain higher total phosphorus. The calcium is the same, magnesium is the same, but potassium and sodium get a reduced concentration in the hydrochar. See the nitrogen, the two nitrogen compounds, if compare raw manure, almost all this hydrochar still have a higher concentration than raw manure, but there are no clear trend. It basically depends on the operating conditions. Sometimes they get higher, sometimes get lower. So this is nutrient distribution in the processed water. So if you compare with the last slide, we see the total phosphorus and magnesium, right, have a definitely reduced trend. The calcium almost similar, and the ammonium nitrogen, I guess, reduced. Both total nitrogen and ammonium nitrogen really depend on the operating conditions. So this is the observation from lab scale test. We see dairy manure can be converted to hydrochar via the HTC process at a temperature as low as 200 degree given enough time. See, longer than 30 minutes, we get a hydrochar. Optimum at 225 degrees C and 60 minutes within our test range. And the phosphorus recovery from manure to hydrochar reached over 90%. Nitrogen recovery was more sensitive to the HTC process, but wasn't our focus at this stage. So to move the lab scale to the more practical application, we designed the continuous flow, the HTC prototype system. So the system was designed to handle continuous flow of manure. We want to make this more efficient for large-scale manure treatment. So the goal, we aim at enhance the economical viability and the feasibility of phosphorus recycling from liquid manure. So the main parts, 2 parts of the system contain the control panel, the left one. The right one is the main reactor, have 2 stages. One's the preheat stage, another I call reaction reactor. So the control panel basically control how fast and get the two reactor reach the temperature. We want to control preheat to 180 degrees C, but keep a reactor at the 200 or 250. By adjusting the flow rate, we can control the reaction time too. Also, they can monitor the energy consumption, the control panel. So in addition, we also developed what we call bench scale or scaling up the batch reactor using a pressure vessel with 2.6 gallon volume with a 6-liter working volume. So with this system, we conduct the test use a bench scale reactor under the optimum condition from our lab scale test. That's 225 degree and 60 minutes reaction time. So this is kind of a comparison. You can see the scale up bench scale reactor. We reach the same, almost the same the hydrochar yield and the phosphorus recovery rate. But in terms of energy input, definitely much lower energy input to the bench scale for producing the same amount of hydrochar, almost just 1/3 of the energy. So yeah, the right side is show the condition we test. Okay, I guess this is the key finding take home. The hydrochar yield and the phosphorus recovery remain stable between the lab scale and the bench scale system. A lower energy input per unit of hydrochar in the bench scale system. So scaling up did not compromise the product output and nutrient recovery. We hope soon we'll get this on a real farm. Definitely appreciate the financial support from USDA and NIFA and the University of Idaho, the P3 I1 grants. Well, thank you for your time. Open